Next you come to the voltage regulation, right. So, voltage regulation of the transmission line may be defined as the percentage change in voltage at the receiving end of the line, right, expressed as percentage of full load voltage in going from no load to full load. That means, that is your percentage voltage regulation, it can be given as this magnitude. Look, everywhere magnitude is there, wherever we will take, it will take magnitude only, but again and again I will not say magnitude, I will just simply I will say receiving end, sending end like this, right. So, it is actually VRNL, that is the receiving end no load voltage magnitude, minus this is receiving end FL, that is a full load voltage magnitude, divided by with respect to your receiving end full load voltage. So, VRFL magnitude into 100, that means where VRNL everywhere mod is there. So, magnitude of no load receiving end voltage and VRFL magnitude of full load receiving end voltage, right. Now, this is that percentage voltage regulation, right. So, it is defined as the percentage change is voltage at the receiving end of the line in going from no load to full load. That means that means that at no load, right, IR is equal to 0. At no load IR is equal to 0. That means your just 1 minute, just hold on. So, at no load when IR is equal to 0, that means in this equation you put IR is equal to 0 in equation 1 say, then you will get, and at IR is equal to 0, VR is equal to VR no load. So, in this equation put IR is equal to 0 and here you put VR is equal to VRNL no load, then you will get VRNL is equal to Vs upon A. This is equation 8, right. So, this is understandable. From this equation only put IR is equal to 0 and VR is equal to VRNL. So, you will get VRNL is equal to Vs upon A. This is equation 8, right. Therefore, this VR no load is equal to Vs upon A you put in the previous equation, that means this equation 7, right. That means in this equation you put VRNL is equal to your Vs upon A, right. So, once you put VRNL is equal to Vs upon A, so it will put and simplify little bit, it will be magnitude Vs, this is Vs minus magnitude A into VRFL divided by magnitude of A into VRFL, this is equal to 100, right. So, this is equation 9. Now, for a short line we have seen that A is equal to 1. So, mod A is equal to 1, mod A is equal to 1, and for a short line VR full load is equal to VR, right. That means this diagram for a short line your VR full load is equal to VR. So, if it is so, then percentage voltage regulation can be written as that Vs minus VR upon VR, all are magnitude into 100, right. So, this is equation 10. Now, using equation 10 and 6 you will get, right, that means in this case that if you go back to equation 6, that means this one, just hold on, this one that equation 6, it is magnitude Vs is equal to this one magnitude VR plus this term, that means magnitude Vs minus magnitude VR is equal to magnitude I into R cos delta R plus X sin delta R. So, in this expression equation 10 replace magnitude Vs minus magnitude VR by this term, that magnitude I into R cos delta R plus X sin delta R, right. If you put it, then it will, this equation will become, that percent voltage regulation will become magnitude I R cos delta R plus X sin delta R upon magnitude VR into 100. This is equation 11. In the above derivation, delta R has been considered positive for a lagging load, right. According to our phasor diagram, we have considered that your for lagging load delta R is positive, this is delta R is positive, right. So, and delta R will be negative for a leading load. Therefore, for leading power factor load, this magnitude I R cos delta R minus X sin delta R, because if delta R is negative, then cos minus delta R cos delta R, sin minus delta R minus sin delta R. So, minus X sin delta R upon magnitude VR. This is equation 12, right. From equation 11 and 12, it is clear that the voltage regulation is a measure of line voltage drop and depends on the load power factor, because this is basically it is a line voltage drop, either this term or this term. This is basically line voltage drop, because magnitude V s minus magnitude V r is the line voltage drop is equal to magnitude I into this term, right. So, this is basically your what you call that is a line voltage drop, and it depends on the load power factor, right. Of course, it depends on the load power factor, because you have to this thing what you call because delta r, this delta r actually it is load current angle, because this is your this is the current I, this is basically current is going to the load, right. So, that means this current is going to the load. So, that's angle, and its angle is delta r, right. This green color is delta r, that means this depends on the your load power factor, right. So, basically it is load angle, load current angle delta r and the receiving voltage, right. It depends on this equation 12. So, this is for short line. What we will do? We will make all this mathematical expression, long line, medium line, and short line, medium line, and long line. After that, we will see the numericals, right. Next is the medium transmission line. Generally, we call that 80 kilometer long, more than 80 kilometer and below 250 kilometer, right, length is a basically we call medium lane lines, and the line charging currents become appreciable, and the shunt capacitance must be considered for the such a long line, right. So, in that case you have to consider the charging capacitance or shunt admittance, this thing your admittance you have to consider. So, now in this case, suppose this is a medium long line and representation by a nominal pi representation, right. That means whatever your charging admittance are there, total charging admittance are there, you lumped on both side half half. That means this side y by 2 and this side y by 2. So, this is called a pi network, and this is the transmission line z is equal to r plus jx, and this is the load, right. So, sending end voltage is V s, receiving end voltage is V r, right, and your what you call, and this is your sending end current I s, right. Here I c 1, I c 2 not shown, right. Current through this is I s, this is I l, and again this receiving end current I r, this is going to the load. This is I l stands for not load, for line, right, and receiving end current I r, this is actually load current, right, and I l stands for I line, this is the line, this is the representation, this way we represent, and this is the load, and receiving end voltage is V r, that is voltage across the load is V r, right. Now, if you now go for this what you call this sending end voltage, now you have to find out sending end voltage and current for the nominal pi model, and in the form of ABCD parameters, right. So, from KCL the current in the series impedance designated by IL is. So, IL is equal to, right, this apply actually at this point right, you apply Kirchhoff's formula, IL is equal to IR, and current through this is that y by 2, that shunt admittance y by 2 into VR. That is why from the KCL this line current IL is equal to IR plus y by 2 VR. This is equation 13, right. You are applying KCL here at this point. So, from KVL the sending end voltage is, from KVL the sending end voltage is in this loop, you apply KVL, right. So, your Vs is equal to will become basically Z into IL plus VR. So, VR is writing fast, this VR actually writing fast. So, Vs is equal to VR plus Z into IL, equation 14, right. Now, this expression for IL, you substitute here, the expression for IL here. If you do so, you will get Vs is equal to, like writing from equation 14 and 13, we get Vs is equal to 1 plus Zy upon 2 Vr plus Z into IR. This is equation 15. So, relationship the sending end voltage with Vr and IR we got, this is equation 15. Similarly, similarly, the sending end current is 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 equal to IL plus Y by 2 Vs. Where is the diagram? This diagram. So, sending end current, this apply your KCL here at this point, Kirchhoff's first law you apply here. So, this is Is, this branch current IL plus Y by 2 Vs, right, Y by 2 into Vs, shunt admittance into this voltage Vs, right. So, in this case you will get Is is equal to IL plus Y by 2 Vs. Now, from equation 16, 15 and 13. So, you substitute here in this expression, you substitute for in this equation 16 is a function of IL and Vs, you substitute IL is equal to this one in this equation and Vs from this expression, Vs from this expression you substitute here. If you substitute and simplify, right, you will get Is is equal to Y into 1 plus Zy upon 4 into Vr plus 1 plus Zy upon 2 Ir, this is 17. So, Vs Is relationship we got in terms of Vr and Ir. Now, put this in matrix form, put in matrix form. So, Vs Is 1 plus Zy by 2 Z Y into 1 plus Zy upon 4 1 plus Zy upon 2 Vr upon Ir, this is equation 18. So, this is A, this is B, this is C D, A is equal to your D, right. So, this is that ABCD parameters for your what you call for medium transmission line, right. So, next is, so the ABCD parameters, A is equal to 1 plus Zy upon 2, B is equal to Z, C is equal to Y into 1 plus Zy upon 4 and D is equal to again A 1 plus Zy by 2. So, we got that your ABCD parameters from the medium your what you call transmission line. Next is that long transmission line. So, for short and medium length lines, accurate models are obtained by assuming that line parameters are to be lumped. For short line in any way we have not considered anything. For medium line we have considered that admittance are lumped both side half half. Another thing for then using that pi method, pi model. Only one thing I would like to tell, we do not use that T network. Suppose if you I am just showing you, suppose you have a transmission line, right. Suppose you have a transmission line and this side is Z by 2 and this side is Z by 2 and if you put Y here and this side is your Vs, right, plus minus, this side load is of course there, but this side is we are not showing the load, just draw this and this is your Y, this is your Y and this is Z to 2, then what will happen, this side if you use a T network, then what will happen, you are creating one additional node, right. So, that means your problem will become more complicated and line impedance we have made half this side, total is Z, this side Z by 2 and if you put Y, then only problem is that we are creating one more node. That means in power system so many nodes, bus bars are there, right. So, many lines are there and for each line then one additional bus bar you will create and this will increase the dimension of the problem. That is why we do not use T network for this or what you call for line modeling, we will use pi method, right. So, that means for long transmission there your what you call, in case the lines are more than 250 kilometer long and for accurate solution the parameters might be taken as distributed uniformly along the line length, right. So, that means at every point that voltage and current will vary from point to point, right, it will be distributed uniformly along the line length, right. And in that case that voltage and currents will vary from point to point on the line. Now, in this section what we will do, this expression for voltage and current at any point on the line will be obtained. Then based on this equation we will try to find out a pi equivalent. First we will go for exact one, then the pi equivalent, right. Now, before going to this, first you look at this diagram, right. This is a long transmission line. Then this distance actually we are measuring from the receiving end to the sending end. This is sending end voltage Vs plus minus polarity shown. This is Vr. This dash dash means is a long line, and from this side we are measuring the distance, right. Now, so what we are doing from the receiving end, total line length from here to here is L, total line length is L. So, from receiving end at a distance x, you are considering a small distance, that is delta x, a small increment, very small, right. So, we are considering delta x. So, at a distance x, this voltage, that means this is x and this is your x plus delta x, right. So, in this case here we are writing that at a distance x, voltage here is V x, right, and for the small length delta x, that it is small y again, it is not total admittance, it is per unit length. Initially when I was giving the nomenclature, I told you small z means it is per unit, it is impedance per unit length, and y small y is impedance per unit length, and delta x is the length, it may be in meter, right. So, this small y into delta x, small y into delta x, that means the small increment we have taken pi model, and at a distance x the voltage is V x, there is a phasor quantity, and at a distance x plus delta x, this voltage is V x plus delta x, right, this voltage, and at a distance the current here is I x plus delta x. This up to this, if it is understandable to you, then everything is understandable, right. That means length will be measured from the receiving end. At a distance x, we are considering a small incremental length d delta x, right, and therefore, for this one, that if we go for the small this incremental thing in pi representation, for example, so this is small y into delta x, at a distance x voltage is V x, and x plus delta x is V x plus delta x. Here the current here at a distance x, here in this section, small incremental section, is I x, right, and this is small z into delta x, small, only for small this section, this is impedance, z is per unit impedance per unit length multiplied by delta x, and this side is I x plus delta x, right, this current. So, and this is V s. So, but this anyway, this is not the sending end, this is small distance x, at a distance x, this small sending end is far away. Similarly, this dash dash shown means receiving end is also far away, right. So, now with this explanation, now this is the figure 4, I told you everything, right. So, it is one phase of a length, this is actually balanced system, right. The phasor voltage and current on both sides of this segment are shown as a function of distance, right. Now, in this case you apply KVL. If you apply KVL this thing, if you apply KVL, then this voltage is V x plus delta x, actually this voltage actually, right, this is V x plus delta x, right, and this is actually V x, right. So, if you your apply KVL here, then V x plus delta x will be small z into delta x and plus your V x, right. So, that means V x plus delta x is equal to small z into delta x into I x plus V x. So, that means V x plus I a, V x plus delta x, this is the voltage here across this, is equal to small z into delta x into I x plus V x, right. So, this equation is written, that means V x plus delta x minus V x upon delta x, right, is equal to small z into delta x. This is equation 19, right. So, that means if delta x tends to 0, if delta x tends to 0, right, this equation, if delta x tends to 0, this equation can be written as no dVx upon dx is equal to your small, your what you call your this thing. Here no, I have missed one thing, that is Vx dx delta x, actually it is Ix, it is Ix, writing error, it is small z into Ix, right. So, that means that dVx upon dx then is equal to small z into I x. This is equation 20 when delta x tends to 0, right. Similarly, so this is equation 20. Similarly, if you apply KCL, then I x plus delta x will be, if you apply KCL, then this is I x plus delta x, this is the current here, apply Kirchhoff's first law here at this point. So, I x plus delta x will be is equal to your I x, that means this current I x, this branch current I x, this segment current I x plus y into delta x into V x plus delta x. So, plus y into delta x into V x plus delta x. So, you are applying Kirchhoff's your what you call first law here. So, I x plus delta x is the current through this is I x plus this is shunt admittance y small y into delta x into V x plus delta x, right. So, this is your current equation. Now, then or you can write I x plus delta x minus I x divided by delta x is equal to y into V x plus delta x. Now, as delta x tends to 0, you can write dix upon dx is equal to y into V x, right. So, delta x tends to 0. So, this is equation 22, right. Now, next you take the your differentiate equation 20, right. If you differentiate equation 20, just hold on, if I where I kept the page number your what you call 13, 14, anyway does not matter, right. If you take the differentiate equation 20, right, and substituting from equation 20, you will get d square V x upon dx square is equal to z small z into dix upon dx, and this dix upon dx, right. You take the derivative of this equation, d square V x dx square is equal to z into dix upon dx, and whatever dix upon dx is here, you substitute in this expression, right. If you do so, you will get that z small y V x, right. That means d square V x upon dx square minus small z small y into V x equal to 0. This is equation 23, right. Next, you assume gamma square is equal to z y, small z small y, that is gamma square. This is equation 24, right. Therefore, this instead of z y in this equation, you replace z y by gamma square. If you do so, d square V x upon dx square minus gamma square V x is equal to 0. This is equation 25, right. So, this is a second order differential equation, right. Now, general solution of this equation, this second order differential equation. So, general solution of this equation, right, is equal to, you can write in general V x is equal to C 1 e to the power gamma x plus C 2 e to the power minus gamma x. This is equation 26. C 1, C 2 all can be obtained by putting initial conditions, we will see just later, right. So, this is equation 26. So, gamma actually known as the propagation constant and is given by gamma is equal to alpha plus j beta is equal to root over j y, because gamma square we have taken z y. So, gamma is equal to root over j y z y, that means your gamma is equal to alpha plus j beta is equal to root over z y. This is equation 27, it is called propagation constant. Now, real part alpha is known as attenuation constant and the imaginary part beta is known as the phase constant, and beta is measured in radian per unit length, right. We will see later on alpha beta, if numerical comes at that time we will see that, right. So, this is next is that your, so now we have to find out the C 1 and C 2, this constant, right, constant we have to find out. Now, from equation 20, that means from this equation, just hold on, from equation 20 means from this equation that dvx upon dx is equal to z into I x. From this equation we can write I x is equal to 1 upon small z into dvx upon dx, right. Therefore, this one your what you call that dvx upon dx, that Vx expression we have got, expression for Vx we have got, this one we have got. So, you take the derivative of this equation dvx upon dx, you take the derivative of this and substitute here and substitute here. You take the derivative of this one with respect to x, and you substitute here, right. So, I am not showing derivative, it is understandable, very simple thing. If you take the derivative and substitute, then you will get I x is equal to gamma upon z c 1 e to the power gamma x minus c 2 e to the power minus gamma x, right. Now, that gamma is equal to root over y z we have just seen, right. Therefore, I x is equal to root over y upon z, right, because it is z means root z into root z, 1 root z will cancel. So, root over y upon z c 1 e to the power gamma x minus c 2 e to the power minus gamma x, right. Now, or we define I x is equal to 1 upon z c 1 e to the power gamma x minus c 2 e to the power minus gamma x, where z c is known as the characteristic impedance, right, and given by this is root over y upon z small. So, z c is given as your root over your what you call z by y, because reciprocal is taken, no, it is understandable, right. So, that means just before moving next, that z c actually root over small z by y is equal to root over z multiply numerator and denominator by L, length of the line, is equal to basically capital Z root over capital Z by capital Y, because it is per unit length multiply L, it will become capital Z by capital Y, right. Anyway, now this is called characteristic impedance of the transmission line Z c. Next is, now note that when x is equal to 0, V x is equal to V r. Look at this diagram. This distance is measured from receiving end, right. So, when x is equal to 0, so V x will be V r, that is V 0 is equal to V r, that is here. Therefore, when x is equal to 0, V x is equal to V r, and from equation 26 you get V r is equal to C 1 plus C 2, right. So, this equation when x is equal to 0, right, when x is equal to 0, your V x is equal to V r, that is C 1 plus C 2 is equal to V r. So, C 1 plus C 2 is equal to V r, this is equation 30. Now, also when x is equal to 0, I x is equal to I r. So, when x is equal to 0, this is the receiving current. So, I x is equal to I r. Therefore, your equation 28, right. So, in equation 28, in this equation, when x is equal to 0, I x is equal to I r, you put it. If you do so, then you will get I r is equal to 1 upon z c c 1 minus c 2, right. So, solve equation 30 and 31 for C 1 and C 2. If you solve it, you will get C 1 is equal to V r plus z c into I r by 2, this is equation 32, and C 2 is equal to V r minus z c into I r by 2, this is equation 33. So, C 1 and C 2 both the constants are evaluated, right. Next, these values of C 1 and C 2 substitute equation 26 and 28, right, because then only you will get the expression of V x and I x. Equation 26 the expression for V x and equation 28 expression for I x. So, we are substituting C 1 and C 2 value. So, this is equation 34 and this is equation 35. Here we are substituting C 1 C 2, here also C 1 C 2, right. So, then these two equation you rearrange this, the equation for voltage and currents can be rearranged. So, first you rearrange the equation of V x. So, V x can be made it like this, that e to the power gamma x plus e to the power minus gamma x by 2 into V r plus z c into e to the power gamma x minus e to the power minus gamma x by 2 into I r, right. Similarly, I x also can be rearranged, this equation can be rearranged. If you do so, I x is equal to e to the power gamma x minus e to the power minus gamma x by 2 z c into V r plus e to the power gamma x plus e to the power minus gamma x by 2 into I r. This is equation 37. That means, V x and I x you got in terms of V r I r, right, by making making all this initial, putting all those initial conditions, right, and we got this expression of V x and I x in terms of V r and I r with some constant, right. Therefore, this term actually cos hyperbolic and this term actually sine hyperbolic. That means, this thing can be written as V x is equal to this term actually cos hyperbolic x, right, gamma x, and this is sine hyperbolic gamma x, right. So, this equation can be written as V x is equal to cos hyperbolic gamma x into V r plus Z c sine hyperbolic gamma x into I r. This is equation 38. Similarly, I x is equal to 1 upon Z c sine hyperbolic gamma x into V r plus cos hyperbolic gamma x into I r. This is equation 39, right. But our interest is the relation between the sending end and receiving end of the line, right. Therefore, but when x is equal to L, V L is equal to V s and I L is equal to I s. So, distance is measured from here, this is the total line length L. So, distance is measured from the receiving end to sending end, right, here it is. So, when x is equal to L, your V L is equal to V s, right. That means, when x is equal to L, V L is equal to V s, and this side also when x is equal to L, at this point your I L will be equal to I s. So, I L is equal to will be I s. So, here we write this equation when x is equal to L, V x is equal to V s and I L is equal to I s. So, V s is equal to, then instead of gamma x it will be cos hyperbolic gamma L into V r plus Z c sine hyperbolic gamma L into I r. This is equation 40. Similarly, I s is equal to 1 upon Z c sine hyperbolic gamma L into V r plus cos hyperbolic gamma L into I r. This is equation 41, right. So, thank you for this one.